All right, this is AP, AB, and BC Calculus. We're doing Unit 7, Section 8. This is the last section of this unit for AP, AB Calculus. There is one more section for AP, BC. So right now, what we're talking about is exponential models and differential equations. So one really common differential equation is exponential growth and decay. So recall that the phrase, the rate of change of stuff, right, whatever the stuff is proportional to the stuff, means exponential growth or decay. So we generally write that, it's usually depending on, it's often a y for your dependent variable and an x or a t for your independent variable, but it doesn't have to be a y. It could be dp dt equals kp, right? So just to show that there are other options, right, I could have something like the rate of change of p with respect to time is kp. That would also be exponential growth or decay, right? So in the next slide, we're going to walk through solving this differential equation once, but honestly, you should memorize the general solution to this particular diff-EQ. This comes up a lot. The AP is not going to expect you to show the work for how you get to this solution because it's so common that it's very typical for students to memorize the solution to this particular diff-EQ. So let's go ahead and walk through how to solve it just once. So we're going to solve this one time, right? We're going to solve dy dt equals ky one time, and then after that, I'm going to suggest that you kind of memorize the solution. So the first thing I'm going to do is separate the variables, right? So the t will move to this side, and the y will move over here with the dy. So I'm going to get dy over y equals k dt. When I do the antiderivative of both sides, right, I get a natural log of the absolute value of y, and on this side I get kt plus that constant of integration c. When I exponentiate to get rid of the natural log, right, I get e to the natural log of the absolute value of y equals e to the quantity kt plus c. But as we've seen before in other videos, I can rewrite that as an e to the kt times an e to the c, and I can argue that this is just a new c, right? So e to a constant is just a new constant, right? So I just called it c sub 1. So you'll see often this general equation, y equals c e to the kt, or c sub 1 e to the kt. Now, as a side note, you can see what would happen if I plug in y of 0, right? So y of 0, the general notation in math for that is y naught, right? Y with that sub 0, right? So if we were to plug in a 0 here, I would get y naught equals c sub 1 e to the 0. So my y naught is just whatever that constant c sub 1 is. So it's sort of a more common version of this equation is to say that y equals y naught e to the kt. Right? So these two are pretty common solutions. It's not cheating to jump from here to this answer. Nobody thinks, oh, hey, you cheated. That's an acceptable thing to memorize. So while you can solve exponential growth differential equations like this, each time, if you need to, you can separate the variables and you can find the general solution. It's a lot smarter to just memorize this. It comes up a lot. So let's go ahead and walk through some problems. So the rate of change of a population is of murder hornets, because, 2020, the rate of change of a population of murder hornets is proportional to the number of murder hornets. So this statement right here, right, that's exponential growth, right? The rate of change of a thing is proportional to the thing, right? So I'm going to go ahead and use H for murder hornets and T for days, right? So basically what I have here is that the rate of change of the number of murder hornets is some multiple times the murder hornets. Well, it's not cheating to say, oh, cool, I get it. This becomes H of T equals H naught e to the kt. That's not cheating. That's great. Okay. So then I'm going to have to use the points I'm given. I'm given that initially there are 10 of those murder hornets, right? So that tells me that H naught is 10. So I now know that H of T is 10 e to the kt, right? But I need k. So in order to find k, I'm going to use this other point that when t is 5, there are 300 murder hornets. So I know that H of 5 is 300. So I can just go ahead and say that that's 10e to the 5k, right? So when I solve, I'm going to divide by 10. I'm going to get 30 equals e to the 5k. Natural log of 30 is a 5k. So my k is going to be a 1/5 the natural log of 30. And if I don't have a calculator, that's really the best I can do. Now that I know k, I can write my answer, that my H of T is 10 e to the 1/5 natural log of 30 times t, right? And that's a little bit squished in there, but you get the idea. So again, what I did is I write the general equation, right? And you can, if you need to solve this diffeq to get this general equation, that's fine, but it really is much faster if you just accept that this is the solution to an exponential growth differential equation, right? And then I'm given 2 points. I'm given h of 0 is 10, or h naught is 10, and I'm given h of 5 is 300, and I use those values to find k. Once I know that, I write my equation. So then a calculator is required for this one. Use your equation from part A to determine the number of the population of the massive horde of terrifying murder hornets after 30 days. So I'm asked to use a calculator to find h of 30. Now, if I don't have a calculator, I could just write in 30 and say, okay, cool, that's the best I can do. I don't know what this is, right? But then I'm going to use a calculator to type this in and get a value. On the AP, we're always going to round to the thousandth place unless we are expressly told otherwise. So 10 e to the 0.2 is a fifth, so it's up to you. I'm just going to write that. Natural log of 30. Notice that the natural log has the 30 in it. The other 30 is not inside the natural log, right? The other 30 is separate. And I hit enter, and I get a very large population of murder hornets. Yeah, so it's huge. That's a lot of murder hornets. We're all in a lot of trouble. That's all I'm saying. 1, 2, 3, 4, 5. That's a lot of zeros. We're going to double check that with a quick screenshot. All right, so let's double check that we have the right number of zeros. That's a lot of zeros. It's a lot of murder hornets. It's not good. It's not good for anybody, right? So, so that's basically the gist, right, of how we're going to do this. Now, you could have, since it is a calculator required here, right, you could have certainly found a decimal for k up here, right? But what I will say about finding a decimal for k is if you find a decimal and you use a rounded answer. So if I had used 0.2 natural log of 30, if I used a rounded answer for k, right, so that's k, right, so that's k. I'm going to store that as alpha a for a sec. If I use the rounded answer, if I use 0.680, for instance, I'm not going to get as accurate of an answer. So if you did 10 e to the 0.680, which is a rounded version of k times 30, right? If I did that, I'm going to get a slightly different answer. So do you see how that's actually significantly off, right? So the reason I mention this is that that answer would be wrong, right? So if you had chosen to use a calculator to get a value for k, right? So you can either leave k as exactly what it is, right? So we'll take a quick screenshot and I'll show you that that's wrong. All right, so the other option, right, is that I stored it as a. So if I had typed in 10 e, and I know this seems like I'm spending a lot of time on this particular concept, I just want to show you how you can get a really significant difference if you're not careful about rounding. Okay, and then that's the right answer. So again, I just want to show you the difference here, okay? So let's drag these over here, okay? So you could either do what I did, right? So you could either do what I did here, right? So this is fine, where I kept this original thing as my k, right? You could either do this, or you could do this thing where you found k, and you say, oh, I get it, k is approximately 0.680, but you use the stored number, right? You use the stored k that I stored in as a, because what I want you to notice is if you round early, so if I had rounded to 0.680 and I use this is very much a wrong answer, and the AP is going to mark it as a wrong answer. So I just want to be really clear that this is wrong. So you have two options. You could either keep k as the entire thing that it was, or you could type it in, since you have a calculator, and get this value, but then use the stored value of a. You can't use a rounded part of your answer for later problems. It's going to cause an issue. So just be mindful. So this is the answer, and then I need units. I need that this is how many murder hornets there are. Also, at this point, if that's how many murder hornets there are, we're all kind of dead. So anyway, Point being, I just want to show you that difference because it is a really important difference, and it's a shame to lose that 1 point on the AP because you use a rounded answer. In a larger setting, when we talk about you getting through the AP exam and talking about just life as a scientist or an engineer, if you use rounded answers early on in calculations, you can see that there's a drastic difference. This is not a small difference, right? This is, a huge difference of number of murder hornets. We're talking in the millions, right? So this is a difference of millions because of a rounding or truncating error early in the problem. So please be mindful that you should use the entire accurate value of a number up until the final answer, which is when you can round or truncate. Okay, so moving on. P1, same idea, but this time we're talking zombies because, 2020, so who knows? All right, so the rate of change of the population of zombies in zombies per day is proportional to the number of zombies. So remember, this rate of change of a thing is proportional to the thing. That's exponential growth and decay. It's not cheating for you to be able to jump to saying that. So if you say dz dt, because z is the number of zombies, is proportional to z, that's exponential growth, and it's going to solve to be z of t equals z naught e to the kt. It's not cheating to be able to get from this statement that I put in yellow. It is expected that you can get to these two statements. That's fine. Now, I then know some other things. I know there were initially 100 zombies. So basically that's saying z of 0, or z naught, is 100, right? And I also know that z of 30, so after 30 days, there are 10,000 zombies, right? So those are the 2 points I know. So I know z of t is the initial population of zombies, which is the 100, e to the kt, right? And then I'm going to use z of 30 to find k. So z of 30 is 10,000, so 10,000 equals 100 e to the 30k. When I divide both sides by 100, I'm going to cross off 2 zeros, and I'm going to get 100 equals e to the 30k. I get rid of the e by taking the natural log, so the natural log of 100 equals 30k. So it seems that my k is a 1 over 30, the natural log of 100. And that's great. That means that my answer is going to be z of t is 100 e to the 1 over 30 natural log of 100. That whole thing is a number times t. And that's my answer to the equation for the first bit, right? Now I'm asked to use it, calculator required. I'm going to use my equation from part A to determine the population of zombies after 60 days. So I want z of 60. Well, that's going to be 100 e to the 1/30th natural log of 100. Remember, that's all a number, and then that whole thing will be multiplied by the 60, right? And then I get an approximate value in zombies, right? I should make sure I have units. So again, same thing. Don't fall victim to the trap where you accidentally round to find a different k. So if you want to find k as a 1 over 30, right? 1 over 30 times that natural log of 100. That's great. Okay, there's your k. That's fine. It's okay for you to say that your k is approximately 0.153 or 4, but you have to use the full number in all of your calculations when you get down here, okay? So I'm going to store that as alpha a, and I can use it as a if I want. That's the easiest way to do it so that you don't have to type this whole ugly number twice. So I'm going to type in 100 e to the alpha a times 60. And that's the easiest way to do this. And I'm going to get that there are 1 million zombies. Okay, that's a lot of zombies. We're all in trouble, right? Now, if you had used the rounded answer, just to show you what would have happened, right? If I do second enter, and instead of using a, if I use, let's say, the 0.153, I'm not going to get the right number, right? So you can't round your answer. So you can either type this entire thing in, or you can store it as a, but to be clear, if you round and use this number, right, you're going to get the wrong answer. So it wouldn't be wrong in this answer to put 0.153, right? But when you type it in, you can't type the 0.153. You have to type the answer, the entire thing. And honestly, if I were you, I wouldn't use the 0.153. I would use the exact answer. It's just a safer plan, okay? All right, moving on. the number of thingamajigs is increasing at a rate proportional to the number of thingamajigs. So again, notice here I really wasn't even trying to hide that it doesn't matter what the thing is. I just called them thingamajigs. This is exponential growth, right? So this is saying, they didn't give me a variable, so I'm going to go ahead and I'm going to call y the number of thingamajigs. Right? And I'm going to go ahead and use t for time. So dy dt equals ky, right? This is exponential growth, right? Which we know integrates to y equals y naught e to the kt, right? So we're told that it takes 5 hours for the number to double, okay? So let's look at what that statement means, because this is really asking you, without a lot of numbers, to find some values. So it takes 5 hours for this thing to double. So let's look at what that means, okay? I do that work over here, right? 5 hours for this thing to double means that y of 5 is double the original value, right? That's what we're saying. Y of 5 is double. So double the original value equals y naught e to the 5k. Well, I can solve for k, right? If I divide by y naught, I'm going to get 2 equals e to the 5k. Natural log of 2 is a 5k. So I now know that k is a 1/5 the natural log of 2, right? That's my number, 1/5 the natural log of 2. So now that I know that, I know the equation, right? My equation for this thing is y equals y naught e to the k, which is 1/5 the natural log of 2 times t. So there's my equation, right? Now I'm asked to use that equation. I'm asked how many hours will it take for the number of thingamajigs to triple? Well, if we do that work right here, right? The question they're asking me is, they're saying y of some mystery value is triple the original. Find t, right? That's what we're being asked to do. We're being asked to find t. So 3 y naught equals y naught e to the 1/5 natural log of 2 times t. I need to solve for t. So I'm going to go ahead and divide by the y naught again. So I get 3 equals e to the 1/5 natural log of 2 all times a t, right? And there are a couple ways I can deal with this. The easiest way to deal with this is just go ahead and take the natural log of both sides to get rid of the e. So I'm going to get natural log of 3 equals 1/5 natural log of 2 times a t. This is all just a coefficient of t, right? I want to solve for t in this whole thing. So I can either divide by it, which is fine. Like, you could write the answer like this. I'm going to say that it's a little unconventional to leave the 1/5 on the bottom like that. That's right. It's not wrong. It's a little weird, right? The better version of this would be to multiply the 5 over and have a 5 natural log of 3 on the top and a natural log of 2 on the bottom. Either way, my answer is that measurement in, I was not given a unit, so it's just units of time, right? Or did I say seconds? Hang on. 5 hours, my bad. I was given a unit. There we go. So my unit of time is 5 hours. So this is the number of hours. Now, if I don't have a calculator, that's my whole answer. If I do have a calculator, I can find the approximate answer, but honestly, unless you are specifically asked to approximate an answer or it's multiple choice, it's better to leave the answer as exact. So there you have it. All right. You're going to go ahead and try the same thing with P2. The number of fruit flies is increasing at a rate proportional to the number of fruit flies, right? Sorry, there's a period there. So I'm going to call F the number of flies, right? I'm going to call T time, which we can see is in hours, right? Because there's 12 hours. So this first statement, the number of fruit flies is increasing at a rate proportional to the number of fruit flies, right? That's df dt equals kf. And it's not cheating to know that that means our equation is f of t equals f naught e to the kt, right? So that's, you want to be able to get this just from that first statement, right? Then we're told that the number of fruit flies doubles in 12 hours. Well, I can use that information to say that f of 12 is double the original, right? So now knowing that, I can use that to find k, right? My bad, it's a 2, not a 12. So 2 f naught equals f naught e to the 12k. I'm going to solve for k, right? So I divide by f naught, which conveniently makes it go away. It doesn't even matter what the initial population of fruit flies are. I'm going to take the natural log of both sides to solve down to that 12k, and then I'm going to divide by 12. So my k, right, my k is going to be a 1/12 the natural log of 2, which means the equation that I need is f of t equals f naught, which I still don't know, but I don't need to know because all of these statements are about multiples of the initial value, right? E to the, and my k is 1/12 natural log of 2, that whole thing's a number, times t. So now what I'm asked to do here, I'm asked after how many hours, so that's a time, will the number of fruit flies quadruple, right? So what I'm asked is f of some mystery value is 4 times the original quantity, find t, right? That's what I'm being asked to do, right? That's the job. So 4 f naught equals f naught e to this ugly k that we found, 1/12 natural log of 2 times t, right? I'm going to divide by the f naught. Again, here it's completely irrelevant what f naught is because I'm getting rid of it, assuming that your fruit fly population is not 0 because you can't divide by 0. But it couldn't be 0 because if you had no fruit flies, then there wouldn't be a problem, right? They can't grow and produce if there aren't any to begin with. So I get this e to the 1/12 natural log of 2. That whole thing's a number times t. I'm going to take the natural log of both sides to get rid of my e, right? And this whole thing is a number in front of the t. So you could either divide this whole thing over. It is not wrong. It's just definitely unconventional. You could write it like this. It's just that's a little bit weird, right? The better answer would be a 12 on the top, right? Because you'd multiply by the 12 first with the natural log of 4, and then you divide by natural log of 2, and that answer is in hours, right? So this is the best version of that answer. This one's not wrong. As long as you include hours, it's just a little weird. All right. So we have 2 more problems. So a calculator is required for this one. So Dr. Olivia Octavius, she's lived to her friends, but Doc Ock to her enemies, is making 2 substances in her lab at Alchemex. The quantity of the first substance, A of t, is changing at a rate in grams per hour modeled by this differential equation. The quantity of the second substance, B of t, is increasing at a constant rate of 8.5 grams per hour. Given that we know A of 0 is 10 grams and B of 0 is 90 grams, at what time are the quantities of the 2 substances equal? So, as with most problems, even though this is calculator, you still have to be able to do some of this by hand, right? So let's look at the 2 different problems we're given. Okay, so we have 2 substances, right? We have substance A, which has this equation, dA dt equals 2a. Well, this is definitely exponential growth, right? Because this is my Ka. So this thing's going to solve to a of t equals a naught e to the kt, but k in this situation is 2, right? And I know what a naught is because I was told that a naught is 10 grams. So I actually have an equation for the first substance. The first substance is 10 e to the 2t. Great, first equation. Let's look at substance B. So in substance B, I was not handed a differential equation, right? But what I was handed in substance B was a statement that B of t is increasing at a constant rate of 8.5. Well, I can translate that into what it means mathematically. B of t increasing at a rate of means dB dt equals, and we were told it's a constant rate of 8.5. I can solve this. dB equals 8.5 dt. When I do the antiderivative of both sides, I get B equals 8.5t plus some constant of integration. I can then use this B of 0 is 90 to find that constant of integration. So since B of 0 is 90, that's 0 plus C. Oh, look, C is 90. So now I have that B of t is 8.5, my bad, 8.5 t plus 90. So now I have 2 equations. So all of that was without a calculator. Now let's get to the part where the calculator is required, because I did say a calculator was required. You're asked, where is the, at what time, sorry, meant to switch colors. You're asked, at what time are the quantities of the 2 substances equal? So what you're being asked is, when is A of t equal to B of t? Well, that's a problem for your calculator, right? So there are 2 ways to do this, right? So option 1 is to put into y1 of your calculator 10e to the 2x, because your calculator uses x, right? And to put into y1 8.5x plus 90, right? And if you do that, you're going to second calc intersect. And that's totally fine. Okay, that's one option. The other way to deal with this is to recognize that what you want when a of t equals b of t. So you could just find when a of t minus b of t is 0, and that might be easier. So the other way to do this is to put into your y1 a of x, right? Now you changed it to x, minus, and then in parentheses, my b of x, right? And then instead of second calc intersect, I can second calc 0. It really doesn't matter to me which one you pick, right? So either this option, where you only have a y1, or this option where you have a y1 and y2 and second calc intersect, you're going to get the same answer either way. So notice that although the calculator is required to physically find the value, you're not solving this by hand, you have to do most of the actual mathematical work yourself. And that's a thing that I think we sometimes miss when we do calculator sections. The calculator can do the number crunching for you, but you physically have to do most of the thinking. So I'll walk through both of these options and you can kind of decide what's best for you. There are definite advantages to each of them. Me personally, I would pick, in all likelihood, the second option. So the reason I'd pick the second option, the pros to the first option, right, are that it's faster to enter in your calculator and there's a lot less thinking. You're genuinely just entering exactly the two functions you have in your second calc intersecting. So I'm going to graph. I'm probably zoomed 6. So here's the problem. Here's the con. I can't see where they intersect, right? So I see this one's somewhere over here, this one's here. I'm guessing they intersect somewhere up here, and I can zoom and change my window, right? The problem with this, so the con to doing this, right, is that it's hard to find the intersection sometimes, right? So it's sometimes hard to find where these two things run into each other, right? So the advantage, so when I'm trying to find this value, I don't know x and I don't know y. The pro to doing the 0 method, right, the reason it's a plus, is I already know one piece of information. I know it's when y equals 0 and I'm only trying to find the x. So instead of adjusting my window both left and right and up and down, I can just adjust my window left and right to try and find values. And also logically, I can make some adjustments, like the fact that, like I can use logical adjustments in a word problem. For instance, time is generally not negative, right? So anyway, so for instance, although I'd be adjusting my windows to find x, I'm not really going to spend a lot of time looking in quadrant 2 and quadrant 3 because a negative x wouldn't make sense in the context of the problem, right? So I'm going to argue that this is the better method. If you wanted to do the second calc intersect method, you would need to go to your window and adjust till you could find where these intersect, right? And you can see that they both go really high up. So I'm just going to see what happens if I go way up to like 300. Oh, I didn't mean 300 for the x. I meant 300 for the y. Come on, brain. Okay. All right, so there's where they intersect. That's not awful, right? I can do second. So I do second calc intersect. I scroll to where they hit each other. Oh, I missed. Close enough. Enter, enter, enter. And there's my intersection. Now, that's fine, right? But again, what's tricky there is I have to find the point of intersection, and sometimes that's easier said than done. So let's drag this here for a sec, and then we'll make it tiny. And we'll answer the question. But I'm gonna tell you that I'm a big proponent of using the 0 method instead. So instead of doing this, right, I'm gonna clear out the second one, and I'm just gonna subtract in parentheses the entire b equation, right? So that's an 8.5 x plus 90. All right, and if I graph that, we'll zoom 6. What you're gonna find is that I pretty quickly can find the same answer. So if I do it this way, I'm going to do second calc 0, and without adjusting the window at all, I was able to find it. So I see that my y is at negative 80, which is why I can't see it. Okay, so now this is tricky. See how my y is at negative 15, but I can't see it? The next time I click, it's at a positive 27. So although I can't see either of those are my two values on either side of 0, and I get the same answer. Again, it doesn't matter how you choose to do this. They're both the same basic skill. It's just sort of a preference thing. There are pros and cons to either. As long as you're able to find the value, I don't care. So if you look, in either case, I get that we're talking 1.150, right? 1.150, and my time in this problem was measured in hours. So the answer, right? So my answer was that b of t equals a of t at t is approximately 1.150 hours. Right? And you should communicate that this is what you're looking for, right? That's an important step to communicate, that you're looking for where the two substances are equal. So somewhere you have to communicate it, right? I need to say this somewhere. Even if I don't use the zero method, I should communicate that I'm looking for where the two of them intersect, all right? All right, let's do one last problem. Again, you're gonna need a calculator for this. Tony Stark is making 2 new alloys for his latest suits. The quantity of the first alloy, x of t, is changing at a rate in grams per hour modeled by the following differential equation, and that's dx dt equals 0.5x. The quantity of the second substance, or the second alloy, y of t, is increasing at a constant rate of 6 grams per hour. Given that x of 0 is 50 grams and y of 0 is 200 grams, at what time are the quantities of the two alloys equal? So, same situation, I basically have two problems, right? So the question I'm being asked, right, this question is when is x of t equal to y of t, right? That's the question I'm being asked. So I need an equation for both of them. So let's start with alloy x, right? And over here, we're going to talk about alloy y. So alloy x has dx dt equals 0.5x. That's definitely exponential, right? Because that's my kx, right? So this becomes x of t equals x naught e to the k, which is in this case is 0.5 t. So it's not cheating to jump there, right? So that's my k. It's also not cheating to know that x of 0 is 50 because that's what x naught means, right? X of 0 is x naught. So I can say that x of t is 50 e to the 0.5 t. So I need to get here. I need an equation for x of t. For y of t, I know that the rate of change of y, right? Y is increasing at a constant rate of 6 grams per hour. So dy dt is a constant 6, right? That means dy equals 6 dt. When I do the antiderivative of both sides, I'm going to get y equals 6t plus some constant c, and I'm going to use the y of 0 is 200 to find c. So c is also 200, right? So that means that my y of t, right, the second alloy that Tony Stark is using, is 6t plus 200. So these are my two equations. I need to know when they're equal, and that's where the calculator comes in, right? So I don't care if you do second calc intersect, right? I don't care if you do y1 is 50 e to the 0.5x and y2 is 6x plus 200, and then second calc intersect. I don't care, right? You can do this, second calc intersect. Or, because you know you want when x of t equals y of t, you could do x of t minus y of t is 0, and that would be that your y1 is 50 e to the 0.5x minus, in parentheses, 6x plus 200. And then instead, you could do second calc 0, right? I don't care which one you pick. You certainly shouldn't do both, right? Notice that calculator syntax. So this thing I wrote here, this is not good for AP credit, right? So you have to communicate in the notation of the problem. I need to communicate that I'm looking for x of t to equal y of t. I can't just say y1 equals y2. That's going to be meaningless in this problem. So I'm going to go ahead and opt for the 0 method because I like that better. Either of them would be fine. Remember, if you opt for the second calc intersect method, you sometimes have to spend a good amount of time adjusting your window. There's nothing wrong with that, but it's just a realistic expectation that we should have. And then that 90 is a 200, right? So you should always double check that your numbers are right. 50 e to the 0.5x minus, in parentheses, is 6x plus 200, right? And I'm going to go ahead and graph. And there's my 0, so I'm going to do second calc 0. And I notice my y's are negative, 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 negative. Okay, now look, they jump from negative 112 to a positive, or sorry, negative, sorry, they didn't yet, my bad. Okay, so they jump from a negative 17 to a positive 3.8. So the negative 17, that's my left bound. Above the axis is the 3.8, that was my right bound, and then I hit enter, and there's my answer. If you'd done second calc intersect, you'd get the same value. The only other advantage to second calc intersect is it does give you what the y value is if you wanted to know how much of each alloy he had. That's an advantage to second calc intersect. This one does not give me that. So my answer is that x of t equals y of t at t is approximately 2.941 or 2, right? You don't write both, you write one or the other. And I believe it was also in hours, but we'll check. Yep, grams per hour, so hours. So that's my answer. All right, and that is the last video in Unit 7. If you are an AB student, if you're a BC student, please hang out for 7-9.